So we're back to our derangements problem. So we can think of the set of derangements as permutations. So this is our hat check problem. And Dn is going to be the set of those permutations of n such that they have no fixed point. So W of I is not equal to I for all I. Okay, and we listed those last time and we found that we had these nice derangement numbers of 0. You can't do anything if n equals 1. There's 1 derangement for n equal 2. There were 2 for n equal 3. Then there were 9, and you can compute that there are 44 after that, and the numbers increase. And so what we want to do is try to get some kind of understanding of these derangement numbers. And one thing to look for is a recurrence relation. So now we want to relate this set dn with dk, where k is less than n. And we don't know how many a priori, we don't know how many terms our recurrence relation is going to have, so we just want to think it through. And what's the best way to think about this? If we have a derangement, we want to think about, if we're relating it down, we want to think about deleting the letter n. So if we have a nice big derangement, something like 2, 5, 8, 1, 4, 7, 3, 6. I believe that's a derangement. We can just quickly go check this. 1, 2, 3, 4, 5, 6, 7, 8. Great, we have a derangement. And now what we want to do is we want to think about how many ways could I take the biggest letter n out of this. So I want to take that out and I want to end up with a derangement. And you can see that sort of plucking it out in this notation is really confusing because these numbers all sort of drop by 1 and you'd see the 4 would drop to position 4. And that's sort of not going to be good. So it's hard to think about it in one-line notation. But another way to think about this condition for derangements is in cycle notation. And that turns out to be a much more fruitful way to think about derangements because what this condition is saying is there are no cycles of length 1. So if I take this permutation and I write it into cycle notation, 1 goes to 2, 2 goes to 5, 5 goes to 4, 4 goes back to 1. What number am I missing? I'm missing the number 3, 3 goes to 7, 7 goes to 3. Wait, that doesn't seem right. Sorry, I'm missing the number 3. 3 goes to 8. That's much more like it. 8 goes to 6. Where does 6 go? 6 goes to 7, and 7 goes to 3. That seems much more doable. Okay, so this is a derangement because there's no fixed point. And now let's again look at the number 8. And now we can see, if we think about this in cycle notation, we could just drop the 8 out of here and we still have a derangement. So the fact that we can delete the 8 and get a derangement, that's the first indication of where our recurrence relation is going to live. So let me write the recurrence relation for you. We're going to have a bijection, dn, and the map is going to be delete n. And this is going to be a bijection with, well, there's going to be some multiplicity. The multiplicity is going to be n minus 1 copies of dn minus 1 union dn minus 2. So let's think about why that's the case. There are 2 cases to consider based on our 2 terms. So the proof of this formula is n is not in a 1 cycle. So n is either in a 2 cycle, it's part of a transposition, or in a k cycle for k greater than or equal to 3. Okay, those are our 2 possibilities. So let's take each one in turn. So first, if n is in a 2 cycle, so what have I got? I've got n, and I've got some letter a, and then what do I have left? This is a derangement. In that there's no 1 cycle in this stuff that's left. So these guys are counted by dn minus 2. It's 2 shorter. So make your cycles, don't have a 1 cycle, and make it 2 shorter. The letter A has how many choices? Well, it can't be n, but it could be anything else. So that is this term right here, of course, with this multiplicity. Okay, so what happens when n is in a big cycle with something else? So now we have n, and we have a1, a2, up to a k minus 1, and now we have a derangement over here. Now, instead of thinking about choosing each of these things and choosing their order, which of course is something you can do, there's a more elegant approach, which is going to be here. Think about it like this. If we didn't have this letter N, the letter N wasn't there, and we wanted to stick the letter N in. So this part here, because k minus 1 is greater than or equal to 2, this is a derangement of n minus 1, right? This is not a 1 cycle, and this is a derangement over here, so all together we get a derangement. And how many places are there to stick the letter N? Well, if we think about it, you can put it in front of any of these letters. There are k minus 1 letters, but it could have been any letters, right? It didn't matter which these which of these A's are. So put N in front of any letter in its cycle. So whatever the cycles are that you have, because it doesn't matter that N was in this cycle, N could have been in any of these cycles. So take your derangement of n minus 1 and pick any of the n minus 1 letters and stick the letter N in front of it. And now you're going to have a derangement where N is going to be in a cycle of at least size 3. So this gives us this second term. And the multiplicity here comes from choose a number to put N in front of. The same thing as here. It's the same concept of choice here, but it's a little bit different. So that's our recurrence relation for derangement numbers. And if we write it in terms of the numbers, we get d sub n is equal to n minus 1 times d n minus 1 plus d n minus 2. And of course, we're going to need 2 initial conditions, so we can take them from here. d1 equals 0 and d2 equals 1. So this is the thing that we have just proved. But we can actually go a little deeper. So let's think about this recurrence, and there's a really interesting formula that we get in addition to this. So let me remind you of what this bijection shows us is that we get dn is equal to n minus 1 dn minus 1 plus dn minus 2. There's another formula we get if we just think about carrying this out. If we just think about doing induction down on this, then we're going to get a corollary that goes as follows. dn is equal to n times dn minus 1 plus minus 1 to the n. So this is a fascinating formula because it's telling us that we're sort of one off from this formula. So let's see this in action. Let's look at d5 is equal to 44. And let's see both of our recurrence relations. So this is equal to d4, which was 9. So, sorry, 5 minus 1, which is 4, times 9 plus 2. Well, 9 plus 2 is 11. This is 4 times 11, which indeed is 44. That was our first recurrence relation. And now this next one tells us that what we get is we take n, which is 5, and we multiply by the previous number, which is 9, and then 5 is odd, so we subtract 1, which is 45 minus 1, which is also 44. So that's kind of fascinating. And we can prove this corollary. I call it a corollary because we can prove it from this theorem. If you just take this guy, leave this guy alone, and now do induction down on this. And that's going to pop out, as you go all the way back down, that's going to pop out another dn minus 1. And so that's going to take this up to n, and you're going to be off by plus or minus 1 depending on the parity. So I'll leave that as an exercise, but this is a really nice way to think about these derangement numbers. Either it's a simple product of n minus 1 times a number, or it's n times a number with an offset of 1. So those are 2 classic recurrences or formulas for computing the derangement numbers. Next time we'll get a formula that doesn't involve the recurrence.